Today's essential question: how did the oceans become what they are today? So please copy down today's essential question at the top of your notes. The topic for this concept is still the development of Earth. But specifically, today we are answering the question: how did the oceans become what they are today? Your first left hand column for this lecture is the formation of the oceans. If we're going to answer the question, how did Earth's oceans become what they are today, we're going to have to start with how they formed. Now, we must understand that early Earth was a very inhospitable, very angry place. The processes that released heat in Earth's interior kept the planet's surface a pool of molten materials. The earliest rocks formed when that molten or liquid material at Earth's surface cooled enough to form a thin, brittle crust. Now, the composition of the early crust was similar to the molten material originating in the planet's interior and brought to the surface during volcanic eruptions, like the same ones that we experience today. All right, first definition for today's lecture: continental crust. Continental crust. Again, this might look like a little bit of a longer definition, but remember, one of your goals is to write down as little as you can while still retaining all the meaning that you require to have a quality set of notes. So, rocks of the crust that make up the base of the continents are referred to as continental crust. Now, continental crust can be anywhere from 35 kilometers to 60 kilometers underneath mountain ranges. The important thing that you definitely want to write down is that continental crust is generally less dense than oceanic crust. Continental crust as opposed to oceanic crust. The portion of Earth's crust that makes up the ocean floor is referred to as oceanic crust. Now, oceanic crust is usually denser and also thinner than continental crust. Now, this is important because of its higher density, oceanic crust will ride lower in the Earth's mantle than continental crust because, again, it's more dense, so it will ride lower. So let's compare oceanic and continental crust. Again, oceanic crust is found below oceans. It consists mainly of basalt rock. And basalt rock, you want to write this down, is composed of iron and magnesium rich minerals. Continental crust, on the other hand, again, is found underneath land masses and is composed of granite. Now, granite, this type of granite has a lot of aluminum and silica. Again, the key thing here is that continental crust is less dense than oceanic crust. Some more definitions. Evaporation. Now, I know that you've all used the word evaporation before, and you know what it means. However, can we articulate it specifically and scientifically? So, evaporation is the process in which matter changes from a liquid to a gas. And so we know that that applies to water, but do we also understand that it can, and in certain circumstances does, apply to other elements? For example, did you know that iron can evaporate? Yes, it is possible to melt iron and then have that liquid iron transition into the gaseous state. Not very common on Earth, but it does occur in other places in our solar system. Next up, sediment. Again, we've already covered sediment, but let's remind ourselves. Sediment is any solid material that is moved by wind, water, or other forces like gravity, if you remember our unit on erosion and deposition. Any solid material that settles on the surface of any land or the bottom of any body of water. So, Earth's oceans formed when the continents began to separate or drift apart. When this happened, material from Earth's molten interior rose to the surface and cooled, producing oceanic crust. As the process continued, water condensed out of the atmosphere, fell in the form of rain or precipitation, then flooded that rifted or ripped apart area. In the new oceans, however, water evaporated, and then rain re flooded the land and entered the ocean. The water evaporated again, and through several cycles. And during these periods of evaporations, rock like halite and gypsum were formed. Now, eventually, coarse grained sediment eroded from the surface of continental crust and covered the deposits remaining after the evaporation. As the spreading of that sediment continued and more water flowed and flooded certain regions, ocean sediments began to collect in newly formed basins. Now, as more oceanic crust was added, the rifted continents were pushed farther apart and the ocean basins grew and they filled with water.
Earth is the only planet in our solar system that we know of with vast amounts of liquid water. Water has always been present on Earth in one form or another. It was present in the rocky pieces that the Earth was built from. And more water arrived here by the bombardment of countless watery comets. Gases that were emitted over hundreds of millions of years of volcanism gave rise to Earth's early atmosphere, which was primarily nitrogen and carbon dioxide. Possibly as early as 4.2 billion years ago, the atmosphere became saturated with water vapor, which became so heavy it began to fall in the first rain. Storms raged and electricity crackled in the skies of early Earth. These early intense rains eventually, over millions of years, gave rise to the first seas. Carving out their place, these huge bodies of water literally gave Earth the first of many distinctive facelifts. Three billion years ago, the key ingredients for another dramatic change to Earth were in place: carbon, methane, ammonia, and water vapor. When energy and water were added to this mix, something startling was created. It turns out that this was the recipe for life.
At this point, we should be able to generate our answer to today's essential question: how did the oceans become what they are today? At this point, please take some time and write your answer to today's essential question in the summary box at the bottom of your notes.